Okay, good morning. So today we're going to start working on the second section of chapter 6, which has to do with the energy of light. We're going to talk a little bit about the relationship between energy and frequency and wavelength. But reminder, what we talked about yesterday was this idea that electromagnetic waves are these oscillatory phenomena found in nature. And there are many different types of electromagnetic waves. There are the ones that are at very long wavelength and very low frequency, which would be radio waves. And then as we progress through the electromagnetic spectrum, we have beyond radio waves, we have microwaves, and then infrared radiation, then visible light, then ultraviolet, and ending up with X-rays and gamma rays, which have the shortest wavelength and the highest frequency. Okay, so these waves are traveling through space at the speed of light. The symbol for the speed of a wave is c. The speed of light in a vacuum is 2.9979 approximately times 10 to the 8th meters per second. And they follow this very simple relationship, which is that the wavelength, which is some measure of the length of the wave using the symbol lambda, times the frequency, the number of vibrations every second that this wave is undergoing, is equal to the speed of light. Okay, so we can use that relationship to interconvert between wavelength and frequency. Now, what we're going to look at is the relationship between light and energy. And it turns out, based on some experiments which we'll describe, one is black body radiation, which was first really the big breakthrough in understanding it was by Max Planck. It was around 1900. And then what's called the photoelectric effect, which was by Albert Einstein. And he described this in about 1905. Okay. And leaving aside all of the history and the details of these experiments and models, essentially what these two aspects of research showed is that light can be thought of as individual particles, which are now called photons. So when light is flying through space from the sun to the earth, we can model it as having a wavelength and frequency. So it is this disturbance of space, these waves, but it's also individual particles. And these particles are called photons. So we can kind of think of light as being a bunch of waves that are discrete, meaning if you break them down to their lowest level, there's individual particles. And you can't break up one photon. So this is not an N, it's a wave. I'm just drawing a little symbol for a wave, right? Up and down like that on those. And each of these little particles would be called photon. And so when we see something, really what we're doing, what's happening is each of these photons is essentially a little energy packet. It carries energy with it. And we're going to talk about how we calculate the energy in a moment. But there's your eyeball. One of these photons will strike a molecule and then cause a cascade effect, which ends up as perception of vision. So you can start asking the question, well, like if light is made up of these photons, you know, what is an individual photon like? And it turns out that there are some experiments that people have recently done where they put someone in a very, very dark place, very, very dark room, and then send photons one at a time directly into the eyeball. And then you essentially guess whether you perceived the photon or not. And it turns out that some people guess right more than 50% of the time. So if they were just guessing, it would be 50-50. They get more than 50, which suggests that some people are sensitive to even one single photon, that they may be able to detect even a single photon. In general, what we're seeing are trillions, quadrillions, quintillions of photons every second. We're seeing lots of photons. Our eyes are not looking at individual photons, but your eye can be trained perhaps, or your brain can be trained to perceive very few numbers of photons, at least a few for sure. Okay, so these are called photons. They're little energy packets, and we can calculate the energy of a photon very simply. So I'm just going to say E sub pH for photon. Very simple relationship. It's H, which is a constant, we'll talk about that in a moment, times F. So here's our second kind of mathematical relationship we've looked at in this chapter. The first one was the relationship between wavelength, frequency, and speed. Now, when we say speed, we can also think of it as the speed of these photons, how fast these photons are moving. It looks like it's the frequency, right? This is just the frequency here. So that means you can very easily calculate the energy of a photon. All you got to do is measure its frequency, multiply it by this H, and you got your energy. So H is called Planck's constant or Planck's constant, Max Planck, as I mentioned earlier. It's named after him. And again, there's a lot of significant digits. This is actually a value that physicists have been very interested in measuring for a long time now. And so H is 6.626. I'm just putting out 4 significant digits, but there's like 9 times 10 to the minus 34 joule seconds. And it turns out this Planck constant ends up being important for all kinds of reasons. And we'll get into some of them as we move along, but it's a very deep constant of the universe. And notice that it's very, very small. It's 10 to the negative third. Now, obviously, the size of a number depends on what the units are. But it's, the smallest number we're going to use in this course is Planck's constant. And that's 6.626 times 10 to the negative 34 joule seconds. Notice the units are energy units, joules, and then time units. So joules times time, okay? Now, if you do the dimensional analysis, what happens is if you put in joules times seconds for H, and then for frequency, remember we said frequency was hertz, but a hertz is a 1 over a second or a reciprocal second. Well, if you multiply joule seconds times 1 over seconds, the seconds cancel and you're left with joules. So that kind of makes sense, right? The energy of a photon, energy units are typically in joules or kilojoules or megajoules or microjoules, some prefix of joules, okay? So there you go, there's your simple relationship. Now, what you can do is you can connect this one also to this one right here. They're related because they both have frequency in them, right? So if I take lambda times F and I set that equal to C, and I say, look, I'm going to solve for F. So I would divide both sides by lambda. That gives me F as a relationship of speed and wavelength. Now I come back in here and I say the energy of a photon is HF, right? Well, here's a relationship for F right here. F is a function of lambda. So we can write this as H times C over lambda. Now, we don't need the parentheses, but I just put them in there to show you that I'm doing the substitution there. So we can get rid of the parentheses and just write it as HC over lambda. Okay, so here's a second relationship for calculating the energy of a photon. So the energy of a photon can be, converted to frequency or vice versa, and it can be converted to wavelength or vice versa. So kind of cool. So we do have 2 constants in here, right? Both of these are constants. These are both important constants in nature. And that's one of the things that physicists and engineers will do, and chemists to some extent, is they'll try to measure the values of these constants so that they can have a better understanding of how matter and energy interact with each other and gain a better understanding of the universe. So these turn out to be very important constants. And again, we'll see H a little bit later on. Okay. All right. So now let's do a little bit of calculations here. There's only really one problem that you're doing with this section, and that is the energy of a mole of photons. So I do want to talk a little bit about dimensional analysis in the units here. So the energy of a photon is very, very low. It doesn't matter what kind of a photon, even if it's a gamma ray, which is the highest energy photon, it's still a pretty small amount of energy. You know, it's not enough energy to move a macroscopic object. But what happens is in nature, you can have large numbers of photons. You can have a mole of photon. A mole is a nice counting unit, right? 6.02 times 10 to the 23rd. So notice that the frequency is directly proportional to the energy. So the greater the frequency of the photon, the more energy it has. So the gamma rays have the highest frequencies, right? They also have the highest energies. Whereas the radio waves have the lowest frequency, so they have the lowest energies. And so if you compare frequencies, I'm just going to put a couple down here. So like, you know, AM radio is, you know, for example, 1010 kilohertz. So that's 1.01 times 10 to the 6th hertz, right? Reciprocal seconds. So that's about 1,000,000 hertz. So on our scale of radio of electromagnetic waves, that's really one of the lower frequencies. And so AM radio was invented, you know, over 100 years ago, and or yeah, about 100 years ago or so. And so owing to its low frequency, the technology at the time was capable of making devices that could, you know, produce these kinds of waves, these very low frequency waves. But if you compare that to, you know, visible light, well, here we're talking about, what is it, 10 to the 14th. So 10 to the 14th to 10 to the 15th hertz. There's a range, right? I'm giving you a range there, visible light. And so that is a very, very large number relative to AM radio, right? Very much higher frequency. And again, the relationship is the energy of the photon is directly proportional to the frequency. So the higher the frequency, the higher the energy. So that means that photons of visible light have energies that are 100 million times greater than the energy of a photon of an AM radio wave, right? You see these big antennas sending out radio waves. The energy of one photon of visible light is equal to the energy of 100 million photons coming from an AM radio station, okay? So the third one, let's think about like a gamma ray, right? So we don't really interact with gamma rays all that often. Well, these are like 10 to the 20, I think. You know, it's like 10 to the 20 hertz. I'm not sure about that number exactly, but again, it's millions or tens of millions of times greater than the frequency of visible light. So what happens is if you start looking at chemical bonds, okay, so lowest energy, right? Let's be careful here, lowest energy. These are sort of intermediate energies, right? And then these are the highest energy, right? There's nothing beyond, as far as we know, gamma rays. So when you start looking at chemical bonds are sort of around the energy of visible light. Not quite. Visible light's a little lower than the energy of a chemical bond, but they're pretty close. And so what happens is if you start looking at energy of, I'm going to do it on a vertical scale. So, you got your radio waves down here. They have the lowest energies. Then you have your microwaves. And then higher in energy, that is the infrared. I'm not scaling this. I'm just kind of ordering it, okay? So, the distance between these lines is not necessarily accurate. And then you've got your visible light, right? And just to kind of remind ourselves a little bit about visible light, it's, violet. Oops, sorry, going the wrong way. The lowest energy is red. And then the highest energy is violet. Remember we said Roy G. Biv yesterday? So red, orange, yellow, green, blue, indigo, violet. So going to higher energies, it goes from red to violet. So violet has the highest energy of visible light. Red has the lowest energy of visible light. And then the next thing you get is, what do you get? You get beyond violet. And what would you call beyond violet? You call it ultraviolet. UV, right? Just as infrared is infra under red. So IR radiation is under red, right? So that's infrared. And then you get your X-rays. And then you get your gamma rays. So those are in energy, but they're also in frequency. So it's energy and frequency. Okay. Now, when we start talking about the strength of a chemical bond, which we haven't really gotten into, we're a little bit ahead of the game in a way, but chemical bonds have energy. And if you can put in enough energy into the chemical bond, you can break the energy. So think of like a piece of chalk, right? A piece of chalk is stable, but if you put in enough force, enough energy into it, you can break the chemical bonds in the chalk and snap it in half, right? So energy is required to break that chemical bond. Well, it turns out chemical bonds are sort of like right in between visible and UV. That's how strong they are. That's how much energy they have. And so any radiation that is ultraviolet or above generally has the potential to break chemical bonds. So there is a protective layer in the Earth's atmosphere called ozone, which absorbs a certain amount of radiation from the sun, ultraviolet radiation from the sun, that is protective to cellular tissue at the surface of the Earth, right? So infrared and microwaves, and for the most part, visible light and radio waves, do not have enough energy to break chemical bonds, at least under most circumstances. There's some tricks you can do, but for the most part, they don't. But ultraviolet, X-rays, and gamma rays, they all have enough energy to break chemical bonds, particularly chemical bonds involving carbon atoms. And so we'll talk more about bond energies, bond enthalpies, we call them, later in chapter 8. But keep in mind that there's a problem coming up in this section, which is discussing the chemical bonds. So there's our ranking from low energy to high energy. And our chemical bond is between visible and ultraviolet. Okay, so let's take a look at an example. Okay, so interconverting wavelength, frequency, and photon energy, right? So wavelength, frequency, energy. It takes 498 kilojoules per mole to break an oxygen-oxygen double bond. Calculate the maximum wavelength of light for which an oxygen-oxygen double bond could be broken by absorbing a single photon, okay? So yeah, 495, 498, that's about the energy. So we're gonna calculate the wavelength of light that has that energy. Now, the thing about this problem is they give you the units in kilojoules per mole. So first of all, it's not in joules, it's in kilojoules, but that's not a big issue because a kilojoule is 1,000 joules. But it's also per mole. So where is this mole coming from? What happens is if you calculate the energy of one photon, it's very, very small. It's like 10 to the minus 19 joules for this type of photon that could break a chemical bond. And so what they do is instead of reporting it as the energy of one photon, they report it as the energy of a mole of photons so that you get numbers that are in the hundreds instead of numbers that are 3.5 times 10 to the minus 19 or 3.4 times 10 to the minus 21, right? So it's just a convenience issue that people will use to make the numbers in the hundreds. It's much easier for people to remember. Oh, how strong is an oxygen double bond? Oh, it's around 500 kilojoules per mole. That's just easier. And if you take organic chemistry, you may even see other units of kilocalories per mole. And so in kilocalories per mole, it's like 120. So they would say the oxygen double bond is 120 kilocalories per mole, but we'll use kilojoules per mole. Okay. So let me show you the logic behind this question or the approach. I'm just going to show you approach. So what we know is the energy of the bond is 498 kilojoules per mole. Okay. And we want to know the energy of the photon so that we can find the wavelength of the photon, right? Hc over lambda refers to the photon, the wave. And so what our strategy is to somehow convert this energy of the bond into the energy of the photon, and then use that energy of the photon to find the wavelength of the photon, the wavelength, right? Remember the wavelength? Trying to find out what the wavelength. And the reason for that is that chemists, for the most part, report photons, generally not in terms of their energy or even their frequency. Sometimes we do frequency, but very often chemists prefer wavelength because of the instrumentation that we use are calibrated in wavelength. Okay. So we will use what are called spectrophotometers or infrared spectrometers, and those devices are calibrated for wavelengths. They're measuring lambda. And there are various technological reasons for that about how we interact with light with technology that we would use wavelength as opposed to frequency. Having said that, there are devices that measure frequency, and there are devices that measure what are called electron volts. And electron volts are actually, even though the units don't seem like it, electron volts are actually a unit of energy. So there are devices that measure energy. There are devices that measure frequency, but for the most part, we're going to use wavelengths. So when you see these problems in section 2 and section 3, you're going to see, and 4 even, you're going to see that wavelength is what's generally being measured or calculated in the problem. Okay. So for that reason, we have to do 2 steps here. We have to figure out how much energy a photon has, and then what the wavelength of that photon is. So the logic here is you have this photon, it's interacting with these 2 carbon atoms that have a double bond. This is the route we represent a double bond. And that energy of that photon is equal to the energy of the bond, the double bond. And if it gets absorbed by the double bond, it will break the double bond, and you'll have 2 carbon atoms that are now separated. The energy of that photon is now in the carbon atoms. So it's absorbed by it. We're getting a little bit ahead in a way. In the next section, we talk a little bit more about this idea of interaction of energy with matter, of radiation with matter. But that's essentially what we're doing. So what that means is you just need to calculate how much energy, this is the energy of a mole of photons. You calculate the energy of 1 photon, and then you can use this formula right over here. So the first step is to calculate in joules the energy of one photon. Okay, so how do we do that? Well, what I'm going to do is I'm going to say that the energy of the photon is 498 kilojoules per mole. And let's just get rid of the kilo. It's 1,000 joules per kilojoule. All right. So kilojoules is gone and we got joules. So you got, I'm going to put it in scientific notation. You got 4.98 times 10 to the 5 joules, right? Do you see how I did that? 1,000 is 10 to the 3. 498 is 4 times 100. Let me see, 4.98 times 100. Scientific notation is a number between 1 and 10. So 4.98 times 100, 100 is 10 to the 2. So 10 to the 2 times 10 to the 3 is 10 to the 5. So now we've got it in scientific notation. Now, but that's per mole, right? So that's still per mole. So what do? We come back to our definition of what a mole is. Hope you haven't forgotten that number. Right? It's 6.022 times 10 to the 23rd. So we want to get per photon. So we could write it this way. 1 mole of photons is equal to 6.022 times 10 to the 23rd photons, which actually has a name. It's actually called an Einstein. It's a unit. You don't see it much in textbooks, but an Einstein is a mole of photons. Okay. So now let's take our 4.98 times 10 to the 5th joules per mole, and I'm going to multiply it by 1 mole divided by 6.022 times 10 to the 23rd. And that's going to get rid of the moles. So now you're going to have joules per nothing. That means joules per 1 photon. Okay. So this number is going to get a lot smaller. You're dividing by 6 times 10 to the 23rd. That's a big number. So you're going to get a really small number. So 4.98 times 10 to the 5th over 6.022 times 10 to the 23rd. And you get 8.27 times 10 to the minus 19. And then just joules, right? So there's your energy of a photon. Okay. That's how much energy it takes to break that chemical bond. So we're also implicit in this problem is we're also actually calculating the energy of a chemical bond, which is kind of cool. So that's how strong this particular chemical bond, the O2 molecule, that's how much energy it takes to break that chemical bond. Okay. Now we want to find the wavelength of this photon. So what do we have? We have this relationship right here. Okay, so I'm going to rearrange it. Lambda is going to be equal to the energy of the photon divided by hc. Okay, so what is that going to be equal to? Well, we have our units, 8.27 times 10 to the minus 19 joules. So there's the energy of the photon that we just calculated. And now we're going to divide that by this kind of messy, right? Really, we're using scientific notation because of these numbers are so small and large. So there's your H, right? 6.626 times 10 to the negative 34 joules times seconds. And then the speed of light is 2.9979 times 10 to the 8th meters per second. Okay. So look what happens to the units. You have joules over joules, seconds over seconds. So 1 over meters. Is that right? Oh, I'm sorry. I did my algebra wrong, right? Good. I'm glad I did that. Sometimes I'll make a mistake on this. Let's come back over here. We're going to multiply both sides times lambda. And that's equal to hc. And then we're going to divide both sides by E. So lambda equals hc over E. There we go. Nice to make a mistake once in a while. Slows you down a little bit when you make a mistake once in a while. So let's rewrite this. So the wavelength is hc over E of the photon. Okay, how did I know that? How did I know I made a mistake? I looked at the units, right? It came out to 1 over meters. Well, wavelength is a length unit, so it should be in meters. So it can't be 1 over meters. So that told me I made a mistake. Okay, so now we're going to have, again, 6.626 times 10 to the minus 34 joules seconds times the speed of light, 2.9979 times 10 to the 8th meters per second. I hope I can fit this in here. And then I'm going to divide that by the energy of the photon, which was 8.27 times 10 to the minus 19 joules. There's a kind of a saying in the sciences, which is if your units are right, your answer might still be wrong. But if your units are wrong, you know your answer is wrong. And that was the case right there. So now dimensional analysis, we cancel the joules, we cancel the seconds, and now we're left with meters on top, right? That's going to be the proper units. Let's see what it works out to. You know, just kind of looking at it, 10 to the minus 25, it's going to be around 10 to the minus 6 meters, just kind of subtracting powers of 10 and adding powers of 10. So 6.626 times 10 to the minus 34 times 2.9979 times 10 to the 8th. Divide that by 8.27 times 10 to the minus 19. And you get, what is that? Minus 8, 2, 4, oh, it looks like it's 7. Looks like it's 2.40 times 10 to the minus 7 meters. Okay. Fair enough. There's our wavelength in meters. It is not uncommon in chemistry courses to convert this to nanometers. Chemists really like nanometers because the instrumentation is in nanometers very often. So we have one more step, which is convert to nanometers. Now, you could, in theory, you could do micrometers too, but typically we do nanometers. So what's a nanometer? A nanometer is 1 times 10 to the minus 9 meters. Okay, so I'm going to take our 2.40 times 10 to the minus 7 meters, and I'm going to convert it to nanometers. So 1 nanometer is 1 times 10 to the minus 9 meters. Meters cancel, you get nanometers, and you get 240 nanometers. Okay. So just kind of looking at this problem, if I can find the explanation they give you, I just want to see what units they put in. Yeah, they converted it to nanometers, 240 nanometers. So that's very typical when you do these kinds of problems, that they're going to want the answer in nanometers. So you do that final step there. Okay. Let me see. Okay, pretty much the same thing. Every time you do it, it's the same problem. They give you the energy and you just want to calculate the maximum wavelength. The reason it's the maximum wavelength is just opposed to the wavelength, it is the wavelength that has enough energy, is that if the photon has more energy, it has enough to break the chemical bond. But if it has not enough energy, so if it has less energy, then it doesn't have enough energy to break the chemical bond. And energy and wavelength are inversely proportional. So what they're saying is, what's the biggest, the maximum wavelength that has enough energy to break that chemical bond? And that's the idea there. So that's why they put maximum in there. So 240 nanometers works, 238 nanometers might work, 236 nanometers might work, but 241 nanometers is too large of a wavelength. It doesn't have enough energy, right? Remember, wavelength, the larger the wavelength gets, the smaller the energy gets. So it wouldn't have enough energy to break that chemical bond. Okay. All right. So the next issue that we come up with is what's called Bohr's theory of the hydrogen atom. So this is 6.3. Okay. And this goes back all the way to around 1905, 1910, maybe a little bit beyond that, a little bit. But Bohr's theory of the hydrogen atom is really often referred to as the first quantum theory. So the chapter is called quantum theory, right? So it's really the first quantum theory that was developed by physicists to explain the structure of the atom. So let's talk a little bit about the history of this so you can see where it's coming from. The issue is the structure of the atom. So around 1900, 1905, the accepted model of the atom was that you had this really dense, heavy, dense particle in the center of the atom called a nucleus. And this is where the protons and neutrons are. Okay. And then outside of that, you had these orbiting electrons. Okay, so this is an electron in orbit around the nucleus. Okay, and so it's moving around, kind of, it's referred to as the nuclear model or the planetary model. Planetary, right? So the electron is analogous to a planet orbiting a star. Okay. The vast majority of the mass is at the center because a proton and a neutron have almost the same mass, but it's around 2,000 times heavier than an electron. So if you have a proton and an electron, you have 99.9% of the mass is in the nucleus, and only 0.01% or 0.1% of the mass is out there in the electron. Now, what was known is that the protons were positively charged and the electron was negatively charged. So that was also known. And so the idea would be that what holds the atom together is essentially Coulomb's law, which says that if you have two particles of opposite charges, they will experience a force of attraction that depends on the magnitude of their charges and depends on the distance between the particles. And we ignore gravity in this calculation, okay? So there's your planetary model. So if we take the simplest element in the periodic table, what's the simplest atom we can come up with? It's the hydrogen atom. And the hydrogen atom only has one electron. So that makes things simple. We don't have to worry about how electrons are interacting with each other. If we want to understand it, we can just look at how the electron interacts with the nucleus. So there's a particular form of hydrogen called protium, Protium, and the symbol for that, the isotopic symbol, is 1, 1. So this has one proton, one electron, and 0 neutrons. So that makes things really, really simple. This is called a two-body system. It's about as easy as things can get, right? How are they interacting with each other? Well, we know the electron is orbiting the proton because the proton is so much heavier. We know they're attracted to each other via electromagnetism, right? The opposite charges, Coulomb's law. There's an interaction occurring there. Now, how do we measure hydrogen atom, right? Like, how do we even know it's around? Well, one way is by using light, visible light in particular. It turns out if you shine white light, all the colors of the rainbow appears white to our eyes. If you shine that onto atoms, they very often will absorb particular colors of that rainbow, of that white light. So what you do is you send in rays of white light. And again, white light has all the colors, Roy G. Biv, red, orange, yellow, blue, indigo, violet. And then you have a nice little container that has hydrogen atoms in it. So I'll just write little H's here for hydrogen atoms. Now there's a little trickiness to this. There's a problem. And the problem is that hydrogen is a diatomic element, so it prefers to be H2. So you have to do a little trick. What you got to do is you got to apply a voltage to it. So you apply a large, you attach a power supply and a high voltage on it. And what that does is the energy of that contained in that electrical circuit is enough to actually break the molecules into individual hydrogen atoms. It breaks the chemical bonds of the H2 and turns H2, which is a gas, into individual hydrogen atoms. So now you can look at the simple system, because otherwise, if it was H2, it'd be a whole different situation. It'd be an H2 molecule, it wouldn't be a hydrogen atom, wouldn't be simple. So you send this light through here and you measure which colors get absorbed. And what you get is this interesting result. You get very specific colors that are absorbed. Okay. You get, this is wavelength on the x-axis. And again, it's in nanometers. You know, really the preference for nanometers has to do with the fact that visible light has a spectrum of 400 to 700 nanometers. This is for visible white light, right? So 400 is violet and 700 is red, the edge of red, and then you go into infrared. So one of the reasons we prefer nanometers is just the numbers are nice, right? If you're dealing with visible light, 400, 500, 600, that's nicer than, 10 to the minus 7. So what happens is there are colors that are absorbed by the hydrogen atoms. So these are the colors absorbed by the atoms of hydrogen. Okay, so one of them is red. And I'm going to write down the wavelength there, 656 nanometers, right? So red is like 640 to 700. Another one of them is green. Oops. $486. Another of them is blue. $434. And then another one of them I don't really have access to this color here, so I guess I'll just put it in black. Is 410. So those are the colors that are absorbed by the hydrogen atom, but not other colors, not 411, not 412, not, there's no orange absorbed. There's no yellow absorbed. It's just a particular color, a very specific color. Because remember, red is like 640 to 700. So we're not saying it's all of the red colors are absorbed. We're just saying one very specific. In fact, they call it a line. So for that reason, This whole thing is called a line spectrum. Okay, because individual lines are absorbed by the hydrogen atoms. Now you can do the reverse of this. What you can do is you can heat up using a high voltage these atoms to the point where they emit exactly the same colors of light. And that is sometimes referred to as an emission spectrum or a bright line spectrum. So sometimes people call it a bright line because it's bright, but they're lines and it's emitting lines. So compare that to a light bulb, which produces all colors or absorbs all colors. This one is only absorbing or emitting very specific colors. And it turns out this is very useful because if you want to look at stars that are around the universe, you can't go there, they're too far. And you can't even go to ours because it's too hot. It'll melt all your equipment and vaporize it. So what do? You measure the light that comes off of stars, right? So you measure them very precisely. And we have these devices that can measure colors really, really well. You integrate over time, measure them every night for a month. And what you can do is you can start looking and see they have spectra. They have these lines. And so each element in the periodic table has its own unique set of lines that it absorbs or emits. So hydrogen, this is the hydrogen one right here. Helium would have its own. In fact, helium was discovered not on Earth, it was discovered on the sun. You know, they got measured these lines coming off of helium. And so that's what actually helium essentially means. Sun, I believe, is what actually the name of the element. So when they discovered it here on Earth, they could say, oh, that's the same thing that's on the sun, which gave them a little bit of insight into what's actually happening in the sun. So each star has its own kind of unique composition of hydrogen, helium, lithium, beryllium, carbon, nitrogen, oxygen. You can kind of study those. You can study each star and see what its composition is and gain insight into that particular star. Okay. Now, the issue with Bohr was that he was trying to figure out, and others were trying to figure out, why a line spectrum. So generally what happens is, you know, if you take a light bulb and you make it hotter, the colors change. Make it hotter, the colors change. Make it hotter, the colors. So like if you take a light bulb and it's like, quote, cold, the light coming off is infrared. If you make it hotter, it becomes red. In fact, if you look at the really early light bulbs, like the ones that Thomas Edison was producing, they're sort of like they're dim, they're not very bright, but they were also sort of like reddish orange. You know, they didn't have white because they didn't know what to put in them. They didn't know how to make them. Tungsten, it turns out, is very useful for making a white light. And so as you ramp up the temperature, as long as you don't break the filament, what happens is the color starts shifting. It goes from red or infrared to red and orange yellow, and then you can make it, you know, white, which essentially means it's so much energy, all the colors are coming off. So the question was, with hydrogen, why doesn't that happen? Like if I just keep heating the hydrogen to higher and higher temperatures, why doesn't it start producing more and more colors and all of the other colors? And it turns out, no, you're just going to get these 4 colors coming off. And so that was a problem. The other issue is like, well, how do you describe what's happening here? Like what's going on in the atom such that it's absorbing these colors specifically? How does that relate to the structure? Like what's happening physically inside that atom? And that's where Bohr had a very good insight. What Bohr came up with was this idea of a transition. Transition. It's essentially the idea that you got your nucleus at the center and then you have your electron. And if a photon has the right amount of energy, the right frequency, the right wavelength, what can happen is that photon can get absorbed by the electron, and that will cause the electron, I'll draw a little arrow here, that will cause the electron to move out to a larger orbit around the nucleus. Brilliant idea. Okay, so now the electron is in a larger orbit around the nucleus. Okay, it takes energy to do that, right? The electron needs more energy to get further away from the nucleus because it's attracted by the nucleus, right? It's in orbit around it. So to move further, it takes more energy, just like a satellite, right? If you want to boost a satellite to a larger orbit, it takes energy. You have to use rocket fuel to move it further away. So same idea. So where's that energy come from? It comes from the energy of the photon, right? That photon has energy. And that's called a transition, where the electron is going from one orbit to another. Likewise, what can happen is that electron might be a little more unstable further away from the nucleus. It wants to be close to the nucleus. So maybe what happens is, on its own, it could jump back down. And when it does that, it gives off the energy in a photon. Remember, the photon has energy, right? So what happens is, the electron jumps back down to closer to the nucleus, emitting. This is called emission. It's emitting a photon. This is called absorption. It's absorbing the photon. Okay? That's called a transition. They're both called transitions, emission and absorption. And that's very useful, right? That seems plausible, perhaps, right? One of the questions that came up was, why isn't any transition possible? Like, why can't I take a photon that has half as much energy and get that absorbed by the atom, and then the electron only moves half as far away from the nucleus? And the answer is that Bohr said it appears as though only specific transitions are allowed. There are only some transitions that are allowed for reasons we don't know, but the data, the evidence suggests there's only very specific transitions that can take place. So he came up with this idea of a model, a theory, that there were certain allowed orbits around the nucleus. And so I'm going to draw a few of them in. These are supposed to be circles, sorry. Now they're actually spheres, right? So it's three-dimensional, but we're just depicting it in 2 dimensions. So these are called allowed orbits, according to Bohr. And he numbered them. And the one that was closest to the nucleus was 1. Further out is 2. Further out is 3. Further out is 4, 5, 6, 7. And you could go as far as you want, okay? Now, because these values are quantized, meaning there are limits on what they can be. They're counting numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, so forth and so on. There's limits on what they can be. They can't be 1.5 or 1.45 or 1.44. We call them quantum numbers. They're quantized. They're discrete values. Like counting numbers are what we call quantized numbers. They can't take on only very specific values, okay? So these are quantized values. N equals 1 or 2 or 3 or 4 or 5. As far as you want to go, he said, you could go up to infinity in theory. But once you're up to infinity, then the electron is gone, right? It's going to be gone. Like once you get far enough away from the nucleus, that electron is no longer part of that atom. So it's gone, right? So we'll talk about that later. Now, one of the things that he was able to do, which was very interesting, is that he was able to do some calculations. And he was able to calculate the energies of these based on the mass of the proton, the mass of the electron, the charge of the proton, the charge of the electron, the permittivity of space, which is a property of space that we use in electromagnetism. And all of those put together, he was able to actually calculate almost perfectly the wavelengths of the spectrum, the 410, the 434, the 486, the 656. There's others, in fact, there's 397. There's some in the infrared, there's some of them in the ultraviolet, and he was able to calculate them using the principles of physics with this particular model. Okay, so essentially, the energy of a given level is equal to minus 2.178 times 10 to the minus 18 joules over n squared. Very simple, right? Now he had some more complicated math behind this, but this is essentially one of the results. That if you want to know what the energy of the electron is in any of those individual levels, it depends on this constant, negative 2.178 times 10 to the minus 18 joules, divided by n squared. So n is 1 or 2 or 3. So if you want to know what the energy is here, or you want to know what the energy is here, you can calculate them. So now suppose you want to know about a transition. Suppose I wanted to calculate the energy difference between level 2 and 3, right? This is 2 and this is 3. I'm going to do it this way. I'm going to say delta E is the difference in energy between level 3 and level 2. Okay, if I'm going from 2 to 3. If I'm going from 3 to 2, I would take the energy of 2 minus the energy of 3. So it's final minus initial. Okay, now let me just go ahead and do this calculation for you. So I'm going to do level 3 minus level 2. So how do we do that? Well, this is going to be 3 for the first time. So what I'm going to do is I'm going to go minus 2.178 times 10 to the minus 18 joules over 3 squared. All right, don't forget that negative. And then I'm going to subtract, but I'm subtracting a negative number. So really I'm going to add, right? Minus a minus. So minus a minus 2.178. So that's plus 2.178 times 10 to the minus 18 joules over 2 squared. Okay. Now, what do we, this is kind of messy. Like, you got these, one of the things we could do is we could factor out the 2.178 times 10 to the minus 18 joules, and then just have minus 1 plus 1, over the 3 and the 2. So let me just show you one way. I'm going to erase all this up here, you guys, just so that I can show you on the same slide. Okay, so if we just factor out the 2.178 times 10 to the minus 18 joules. Now, if I factor this out of the first term, I just have minus 1. And then if I factor that number out there, I just have plus 1, right? If you take the number out, you just have 1 left. Now, that kind of looks a little funky, okay? Right? It looks a little bit funky. It'll give you the right answer. Okay. But another way to do it would be to say, minus A plus B is equal to B minus A. You know what I mean? So you could do this. Since this is going to be minus and this is going to be plus, you could just reverse the order and just say 1 over 2 squared minus 1 over 3 squared. And that would work. Okay, so now that you have that, we can generalize that into a formula, which is that delta E is 2.178 times 10 to the minus 18 joules times, now we're going from 2 to 3, so it's 1 over the initial values squared minus 1 over the final values squared. So that works also as a general formula. Okay, but let me go ahead and do this calculation. Just be careful. You got the parentheses. So I would recommend doing the parentheses first, do the operations in the parentheses, and then multiply by the constant. So 1 over 2 squared is 1 over 4. Minus 1 over 3 squared is 1 over 9. So you get 0.1388. Yep, that makes sense. Times 2.178 times 10 to the minus 18. And you're going to get delta E is equal to 3.025 times 10 to the minus 19. And then the ends don't have units, so it's just joules because this number here has a unit of joules. So there's your delta E. Now, here's Bohr's model. He says that to get the electron to go from the second to the third level, you put a photon in. And that's called absorption. And if the photon has the energy difference, its energy is equal to the energy difference between 2 and 3, which we just did. That's what that calculation of delta E is, the difference in energy between 2 and 3. If the energy of the photon is equal to that energy difference, there's a matching process that takes place, and the photon can be absorbed by the atom, by the electron, to promote the electron up to another level. So now this photon goes out of existence. It's no longer existing in nature. It has been transformed into electromagnetic energy of the electron, which is its physical orbit around the nucleus, right? So it's kind of trippy here. We're saying, yeah, this photon has energy, which is an electromagnetic disturbance. The electron is electrically charged, so it can interact with it because it's electrical. It absorbs the energy completely of that photon. The photon no longer exists. The electron is now promoted to a higher level and now has a different orbital. So there's like, think about it, that's kinetic energy. Its orbital kinetic energy is different than it was before, all because of that radiation, right? So cool stuff. So what does that mean? If it's a photon, that means we can calculate wavelengths. So let's calculate a wavelength, right? So this delta E is going to equal the energy of the photon. So we did this calculation earlier, hc over E, right? The wavelength of a photon is hc over E. So if we put those numbers in, I'm just going to go through and do this real quick. So there's your H. There's your C. And then here's our E, 3.025 times 10 minus 19. I'm not going to go through the dimensional analysis here, but remember, H is joules seconds, C is meters per second, and then energy is joules, right? So it's all going to cancel out to give you meters. So let's see what we get. 6.626 times 10 to the minus 34 times 2.9979 times 10 to the 8th divided by 3.025 times 10 to the minus 19. And you get 6.57 times 10 to the minus 7 meters. Okay. It's 6.567. All right, let me write that with an extra digit. Okay, there you go. There's your wavelength. Now, just to remind you, that corresponds to our spectrum. 410, 434, 486, 656. So that calculation right there, 656, you can see it right there. That corresponds to that one right there. Our line spectrum, right? This is the hydrogen line spectrum. Okay. So Bohr's calculations were very good. And I didn't talk about ultraviolet and infrared very much at all, really. But there's other lines that can be measured in different, regions of the electromagnetic spectrum that Bohr's model also was able to predict. Okay. So there you go. So that's an introduction to the Bohr model. That's the first type of problem. And what we'll do next week, I'm sorry. What we'll do next week is we'll start looking at more of these Bohr calculations, more of the Bohr model. I gave you everything right there, but we'll go back and look at some of the problems in more detail and practice those. And then once we've got that, then we'll get into even the more interesting stuff, which is the wave property of matter. And we'll look at that as well. So have a great day, and I'll talk to you later.